Okay, problem 2 of the 3 common Gauss law problems is the infinite sheet of charge. I'm doing this one before I do the line or cylinder of charge because that's, I think, the hardest one. So the sheet has an area density or a charge density of sigma, which is a surface density or an area density. Fine, that's what I called it. And it's charge divided by area. So the units might, for example, be coulombs per square meter. So here is, I'm going to draw a side view of the thing. So here is your sheet of charge. I'm going to say it's positive, although in reality it could be positive or negative. This here is sort of the 3D view of one area chunk of it that has an area of A and a charge of Q. But what I want to show you the side view here, so let me just do that and say here's my origin. There is my x-axis. My y-axis goes up like that, and then the z-axis comes out at you. So this is a side view, but it'll give you the ideas. So we start with symmetry. What do we know from symmetry? Well, from symmetry, we know, so symmetry tells us, first of all, it tells us that the electric field can't go in the y direction or the z direction. Remember, this is an infinite sheet of charge that fills the y and z plane, so it's perpendicular to the x-axis. Okay, so if the field had like some upward component, then you'd be able to do a change of coordinates where you just spin everything around the x-axis and turn it into a downward component. But the universe shouldn't care what your coordinate system is. So symmetry we can use to basically prove that the electric field has to be in the x direction only. So this is like what we did with the sphere. This E could be positive or negative. It can possibly depend on x, but not on anything else. Why can it not depend on anything else? Because if you're talking about a point, say, here, then you know the how far away this is in the x direction, but you don't necessarily have any reason to believe you're at any particular y or z coordinates, because the entire sheet of charge is infinite. There's no edges to refer to. You can't tell you're facing. You can't tell and you can't tell where you are on the sheet. You could be, if you're here, you could be down here. You wouldn't know. You could be down here. You could be down here. You could be at any point that's at the same distance from the sheet. So I'm going to call this distance you are from the sheet, I'm going to call it D, okay? And so let's see, let me say that in addition to knowing that the field has to be along the x-axis, we also know that magnitude can depend only on your x position. Okay, I'm not sure why I called this D. There's no real need for that. But anyway, so what I'm going to do is say we're at this point here, which has some x coordinate. We know the field has to go either this way or the other way. So what I'm going to do now is set up a Gaussian surface that goes through there. And so we can just pick any Gaussian surface that has an area of A and is parallel to the sheet. And we know then that the electric field all over this surface A, or with area A, will have the same electric field everywhere. Therefore, so let me take 2, Gaussian surface is going to be an area A parallel to the sheet of charge at a distance x. Okay, at a distance x. Okay, now this is not a closed surface, obviously. So what we can do here is we can pick a mirror. A mirror sheet over here. Okay, that also has an area A. Okay, at distance x. Okay, so our first, also at a distance x, but in the opposite direction. Okay, So there we go. And now we can say that we have this area A that I first described here, plus another identical area at negative x. So that's this one over here. And now you have these two surfaces that are parallel to the sheet. In fact, I could draw them, well, let me draw one like that, and one over here like that, okay? And now we just need to connect them together. So you basically create a rectangular prism, or if you made these circles, which might be easier, you just create a cylinder whose axis lies along the x-axis, okay? So we have this area, so this area here, we have this area here, and plus, I'm just going to say side walls of a rectangular solid. Okay, if you feel like this is too fancy terminology or too general terminology, you can just settle on a cylinder. I mean, you're the one who's going to have to derive this on the test, so by all means pick whichever one you feel most comfortable describing. Now that I think about it, probably a cylinder would have been the easiest thing, but whatever it is, it doesn't matter what the shape is. All you need to do is say it's a shape that has this area A. Okay, so here this guy has the area A and this guy has the area A. Okay, so next, now that we've defined these guys, I want to talk about the flux on them. Or actually, let me talk about the surface normals first. So this guy, the front face, has a surface normal pointing in the positive x direction, which means it's equal to I hat. This guy here has a surface normal pointing in the negative x direction, which means it's equal to negative I hat. And here we have a surface normal on all of these sort of connecting sides, the side walls of the rectangular solid, as I said. We have an n hat equal to some combination of I hat, or sorry, an n hat that is perpendicular to I hat, okay? So, I'm sorry, what I meant was it's equal to some combination of j hat and k hat. It can point in the y direction and the z direction, or some combination of thereof, but it has to be perpendicular to I hat, okay? So what that means here, I think I've done enough. I wish I could carry a drawing over, because this one's the hardest one to see. But, so I'm going to go, I'll probably have to refer back to that. So, for step 3, I'm going to find the flux through these 3 different surfaces. Or, you know, well, yeah, okay, these 3 different surfaces, or the 3 different types I've described. So, I'll say the flux through what I'm going to call the right side, okay, phi r, is going to be the flux through the right side. So let me just point this out to you and say that is the flux through this, okay? Okay, and we know that, okay, so it's going to be, we know that the electric field along that surface, because that entire surface is a distance x away from the sheet of charge, so we know that our electric field everywhere there on that surface is going to be constant. So that means we can go ahead and use this formula here. We don't have to do an integral. Unless your teacher says you have to do an integral, in which case do an integral, okay? So that's going to equal A, and then we said the electric field there is defined like this. So we know that it goes in the x direction, and then we also know that I hat is, or sorry, we know that n hat is equal to I hat there. So that means our flux through that right-hand side is going to be A times E, okay? Now flux through the left-hand face. Okay, so it's got the same area. Now, what we can say, we actually have not talked about this, but we know that if the electric field here is E times I hat, over here, by symmetry, and I'm just going to draw this in red even though it violates my color scheme, oh dear. By symmetry, wow, I'm doing great. Symmetry, S-Y-M-M-E-T-R-Y, symmetry, it has to go the opposite direction but have the same magnitude. So, because you're the same distance away, here you're a distance x away on the right-hand side, and you're saying it's going E, well, it's got a magnitude of E and goes in the I hat direction. Here you're a distance x away on the left-hand side, So this has a magnitude E, and it goes in the negative I hat direction. Okay, so what we can say here is that this left face that I just pointed out to you has the same area as the right-hand face. Well, I guess I'll just say do this again, okay? So same area, but then the field over there is negative E I hat. And what did we say the normal was over on that side? It is right here, normal on that side is negative I hat. So going, oh, our kittens are getting rambunctious. I'm going to have to go play with them after this derivation. Okay, so we do this dot product. Well, again, I hat dot I hat is 1. The negative signs cancel out. So again, you get AE. So this is important. If I just do a little sketch here, here's your charged surface, okay? Here is the right-hand side Gaussian surface, part of your enclosed Gaussian surface. Here's the left-hand part of the Gaussian surface. And we're saying out here, there's flux outward equal to A times E. And here there's also flux outward equal to A times E. And the reason why they're both flux outward is because the enclosed surface looks like that. So even though the field reverses direction, the unit normal vector also reverses direction. That's why you have the same flux through both sides. And then lastly, I'm going to do the flux through the side walls. Okay, so that's through all of the walls that are facing in the Y and Z directions that are perpendicular to the left and the right walls. And these are the ones that make it a rectangular solid. Okay, so again, A E dot N hat, and this is going to be, well, whatever the area of those walls is. And then we know that the normal vector there is perpendicular to I hat. So this could be, I mean, let's see, the field here is going to point outward or inward, okay, towards the solid sheet of charge, not solid, but the sheet of charge. And we know that therefore it's going to be parallel to these side walls, which means that the dot product of the n hat normal vector with the electric field at those points will be 0. So the flux through those is going to be 0. Let me just back up one and show you. That's like the sidewall here, and we know the electric field can only go in the x direction, but we know that n hat is perpendicular to I hat, which is the unit vector in the x direction. So that means that the field will always be running parallel to these sidewalls, which means that there will be no flux. So there you go. Now, the electric flux out of the thing is going to equal phi L plus phi R plus phi from the sidewalls, and that is going to equal 2 times A times E. Okay? I'm doing it this way so we can just get the result for a single sheet of charge. It's a little more confusing when you have multiple sheets of charge, or a solid object with a sheet of charge on one side. So let's go baby blue for the end. Okay, so for the wrap up, finally, I'll just go down here. Gauss's law says that electric flux out of this closed surface is equal to the enclosed charge divided by epsilon naught. Okay, so now your flux through that enclosed surface is 2AE, and your charge enclosed is Q, so you divide that by epsilon naught, and so what you'll get is that the electric field, let me go down here, the electric field is going to be equal to Q over A epsilon naught. Q over 2A epsilon naught. Or, it's more appropriate because Q over A was the, sorry, my handwriting sucks here, but is the charge, my handwriting stinks, sorry, is the charge density, the area charge density sigma. So what you really should get, and I'm just going to go ahead and render this, no I'm not actually. So I'm going to say E is equal to sigma over 2 epsilon naught. Okay, so there you go. There's a question about why this is different in a conductor. And that's a sort of confusing question. I will try to address it in a separate video, I think, because this one's already pretty long. But This is for just a single sheet of charge or one side of an insulator that's charged, whatever. So there you go. Hope that made some sense. And the last one will be coming up.